Greetings everyone. So today in this video we are going to discuss about the carboxylic acids. First we need to understand that what does the term carboxylic acid means, what sort of functional group it is. It is basically a mixture of two functional groups. Number one functional group is the carbonyl group and the other functional group is the OH group, which is the hydroxyl group or alcohol group. Now both of them combine together, and that when we write them together we call this group as a carboxylic group. This carboxylic group, carb is taken from carbonyl and oxyl taken from hydroxyl, and that's basically what makes it give its name. Now, when we look into the structure of carboxylic group, when you're going to look at carboxylic acids, they are acidic in nature. They are the most acidic um, organic acids, right? So let's just understand a few basic things about carboxylic acid. First, we need to just look into a few basic structures. We have gone through the nomenclature, but we are going to look into some of the basic structures. This structure is of methanoic acid. This is a structure of a carboxylic acid known as methanoic acid because it is having one carbon. It's formic acid. Also, this one is acetic acid, the most important carboxylic acid. Propanoic acid, and then we have the butanoic acid, also known as butyric acid. Butyric acid is found in cheese as well as in milk and dairy products, which gives it its characteristic aroma. And on the other side, we have the pentanoic acid, valeric acid, which is used in a lot of different. It is basically having a strong smell, so that is why it is given the name valeric acid, and caproic acid, which is hexanoic acid. Caproic acid. That caproic acid is the found in the milk of goat, due to which we named it as caprion. Caprion in Greek means goat, so because it was first isolated from the milk of goat, so it is known as it is known as caproic acid. So let's just move on to some of the important things about their structure. If we just look into the structure of carboxyl group, having a very diverse structure. Let's say I draw a carbon here, I draw an oxygen here, and I draw oxygen here, and I draw an hydrogen here, right? These are the atoms which are present in the carboxyl structure. So what I'm going to draw first is the carbon which is present in the carboxyl group. It is sp2 hybridized. Sp2 hybridized, right? It is an sp2 hybridized carbon. So let me just draw the sp2 hybridized structure. This is sp2 hybridized structure, right? So this is the three sp2 hybridized orbitals. I'm going to write over here sp2, 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 right? And alongside that, if we just talk about the structure of the oxygen of the hydroxyl group, oxygen of hydroxyl group is going to have an sp3 hybridized orbital. Surprisingly, it is an sp3 hybridized orbital, right? So I'm going to write here sp3, sp3, and two more sp3 orbitals for the lone pair, sp3, sp3, right? And let me just write one more orbital. Let me make one more orbital. This is for the oxygen of carbonyl carbon. Now the carbonyl group is having oxygen which is sp2 hybridized. This is sp2 hybridized, sp2, and then we have two sp2 hybridized, other two sp2 hybridized orbital. Let me just bring it a bit closer. So it should come here. Yes. Now if you just look here, I am drawing one sp2 hybridized orbital here, sp2 hybridized orbital here. So one thing, this is another thing, right? So these are two sp2 hybridized orbitals which are having the lone pairs, and then it's the final thing which we have to draw is the pi orbitals. This is pi orbital of oxygen of carbonyl group, and this is a pi orbital of carbon. Pi, pi, the bond being made, so the bond being made, right? And these are pz orbitals, right? Two pz orbitals. So this is the pi bond which is formed. Now one more thing over here. This is the s orbital of hydrogen of the hydroxyl. So if you just see the entire structure, the structure of the carboxyl group is pretty complicated, so we won't find it much in any of the books. But one thing which is worth considering is that it is a mix of both groups, mix of hydroxyl group and carbonyl group, which means that it exhibits both. If you just look it into from the perspective of an alcohol, it is having a tetrahedral structure. The oxygen is having a tetrahedral structure. But if you just look from the carbonyl group perspective, it's going to have a trigonal structure, and the bond angle would be varying again with the with an independent bond as well. So that's the point to consider. Let's move on to state, that what sort of state it exists in. So from C1 to C3, it exists in colorless liquids, and it exists in colorless liquids, and it has a pungent smell. A pungent smell is there from C1 to C3, while from C4 to C6 there's a better smell, but that is also unpleasant, and there's also colorless liquid, right? And then till C20 we are having liquids. After C20 we have solids. And if you just look into its solubility from C1 to C4, the solubility is found to be highest solubility from C1 to C4. So if you just compare carboxylic acids, they are having the same trend of solubility as alcohols, such that when there is an increase in the number of carbon atoms, the solubility decreases as it does for alcohols and carbonyl groups. But the thing is that over here there is an increased solubility as compared to alcohol. If let's say if I take two compounds, I take on one hand side I am taking ethanoic acid. Ethanoic acid, on other side I am going to take ethanol. So which one is supposed to have more um, of the solubility in water? Then the solubility which is going to be more in water is ethanoic acid. Why? Because ethanoic acid basically has the carboxyl group, which means that it is having two polar groups. OH group is one polar group, and there's oxygen group which is another polar group, which makes it extremely soluble in water. And that's again an important thing. And if you just talk about another important thing that I would like to share is that over here we are going to consider the melting and boiling points. If we just look at the trend of melting and boiling points, again it's similar with alcohol, such that it increases with the increase in the number of carbon atom. But there's one thing that needs to be considered, that whenever we are going to dissolve carboxylic acid, I take a carboxylic acid, right? I take a carboxylic acid and I dissolve this in water. I put that carboxylic acid in water. What will actually happen is that carboxylic acid will exist in an aqueous solution as a cyclic dimer. Cyclic dimer. And how is that structure formed? It is in this diagram. You just see this diagram over here. You are actually seeing two carboxylic acids which are in the form of a cyclic dimer, right? Over which the two carboxylic acids are joined by weak hydrogen bonding. Weak hydrogen bonding. This is one carboxyl group, other carboxyl group. Both are joined through weak hydrogen bonding. This is a cyclic dimer, and we call this cyclic dimer as the packing efficiency, right? So what actually happens is, in a carboxylic acid, the boiling point and melting point increases irregularly, which means that even number of carbon atom, if there is a carboxylic acid which has even number of carbon atoms, then it is going to have more melting and boiling point, more melting point than odd number of carbon atoms. What does this mean? This means that if I let's say I take formic acid. formic acid will have an let's start from ethanoic acid. Let's say I take acetic acid. Acetic acid will have more melting and boiling point than formic acid. And then I take propionic acid, that's going to have less melting and boiling point than the acetic acid. Then I'm going to take the butanoic acid. Then butanoic acid would be having an increased melting and boiling point than both of them. And then we are going to have let's say pentanoic acid. Pentanoic acid will be having a melting and boiling point less than the butanoic acid. So in that way, there will be an irregular sequence of melting and boiling points, right? And why is that so? Because there's a thing that even number of carbon atoms have more packing efficiency, such that they whenever we are going to have an even number of carbon atoms, they are going to pack more efficiently, and they are going to make cyclic dimers more easily, due to which their packing efficiency would be more when there are even number of carbon atoms. But if there are odd number of carbon atoms, it becomes much more difficult, due to which the odd number of carbon atoms in carboxylic acids are having a weak melting and boiling point, while the even number of carbon atoms are having much more of a strong melting and boiling point. And this is all about it. Now let's just move on to some of its acidic characteristics. So carboxylic acid is a very acidic acid. I mean, if we just compare carboxylic acid with phenol, water, and alcohol, then we will find that this is the order of acidity. Carboxylic acid is most acidic. It is having the lowest pKa value, which is 5, and then phenol is having somewhat around 10. Water is somewhat around 15.7 something, and alcohols are having something around 16 to 20. It varies with the number of carbon atoms. So uh, carboxylic acids are having greater acidity than phenol, water, and alcohol, but they are having less acidity than mineral acids. Mineral acids like HCl and H2SO4 are more acidic than all of these, than carboxylic acid, phenol, water, and alcohol. So this is an important point to consider. Now, if you just look into the carboxylic acid, can we can classify the acidity of carboxylic acids by two important things, such that let's say I draw the structure of a carboxylic acid. Now, in this structure, when I'm going to increase the number of electron withdrawing groups, when I'm going to increase the number of electron withdrawing groups, like when I'm going to increase the number of electron withdrawing groups, then at that point I'm going to increase when I'm going to increase the number of electron withdrawing groups, I'm going to actually increase I'm going to increase the what actually an electron withdrawing group does. Let's say I take an electron withdrawing group, I take chlorine, right? I take chlorine, and that's more electronegative, and when it's going to be placed in let's say it is placed in place of hydroxyl group. Let's say I'm having this. What actually chlorine will do is chlorine will take away the entire it will bring the entire electron cloud of carbon towards itself, right? It will bring the electron cloud of carbon, electron cloud of oxygen towards itself, due to which this would be this would be making the carbon more electropositive. It is going to make the carbon more electropositive, and it is going to make, due to this reason, the carbocation which is going to be formed, right? Let's say when it is going to, be more, it's going to pull away the entire electron cloud. The carbon which is going to be um, placed over here, this carbon is going to have formation of a more stable, I'm just writing over here, more stable carbocation, carbocation, right? It will form more stable, sorry, not a carbocation actually, but a carboanion. It's going to create a more stable carboanion, right? And that carboanion, when, all right, one more important thing I just forget to mention here, this is going to be, this is the actual structure, it's OCl, not the Cl only. Cl will pull away the electron cloud of oxygen, due to which it will decrease the electronegativity of, it will actually decrease the electron density around oxygen, due to which it will form a more stable carboanion. Whenever I'm going to take away the chlorine, then I'm going to form a more stable carboanion. And that more stable carboanion can easily give away its proton. When the carboanion is more stable, it's going to give its proton, or the positive agent, more easily. And it is due to this reason there would be an increase in acidity whenever I'm going to give an electron withdrawing group to a carboxylic acid. For example, if you just take in this example, this is an example of an acid halide. This is an acid halide. Acid halide is 100 times stronger than a carboxylic acid. It is 100 times stronger than a carboxylic acid. This is a point to is worth considering. And there's another important thing that I like to share, which is about the electron donating groups. Electron donating groups are going to have the opposite effect. Electron donating groups are going to have the opposite effect. How are they going to have an opposite effect? The opposite effect is that, let's say I take an electropositive agent. That electropositive agent comes, and that basically increases the electronegativity of oxygen, due to which electron donating group, let's say I add a methyl group over here, R C O and then OR. So here, let's say I take a methyl group, I, instead of R, let me write a methyl group. So over here, what I'll actually get is the electron, methyl group is an electron donating group which will donate its electron towards the oxygen, due to which it will become more electronegative and thus become more unstable. It will become more unstable, and because it will become more unstable, it would be less likely, less likely to give away its electrons. It would be less likely to give away its electrons and proton, actually. Not give away its electron, but if I were to mention it, its protons. Give away its protons, right? So, and due to this reason, it would be less acidic. So this is all about acidity. If you are going to have an electron donating group, then that is going to decrease the acidity. The electron withdrawing group is going to increase the acidity. Now let's take example of an electron donating group. Let's say, instead of, whenever you're going to have, let's say, a higher carbon chain. Oops. Let's say if I'm going to have a higher number of carbon atoms in a carboxylic acid. On one hand side, I'm going to have, let's say, on one hand side I'm going to have formic acid, and on the other hand side I'm going to have acetic acid. Then the acid which is going to have more acidity would be formic acid. Formic acid is more acidic than acetic acid because acetic acid has more number of carbon atoms, more number of methyl groups, due to which it is less acidic. So when we are going to increase the number of carbon atoms in a carboxylic acid, then the acidity would be decreased. This is the trend. Alright, now let's just move on to another thing. Alright, so over here, let's understand the reactivity. Reactivity of carboxyl group is such that if you just look at its structure, we just basically see that this is an electronegative oxygen, right? This is electronegative oxygen which is pulling away the electrons of carbon, and there's another OH group which is pulling away the electrons of carbon, due to which the carbon which is present over here becomes highly electropositive. This highly electropositive carbon, this highly electropositive carbon then becomes a highly reactive agent, and the reactivity again it the reactivity decreases with the increase in the number of carbon atom, such that when you are going to increase the number of carbon atom, then the reactivity would ultimately be decreased. And when there are more number of carboxylic acids, then it becomes more the compound becomes more reactive. Now, there are three major types of reaction due to this reason, that because of the presence of this highly reactive electrophilic carbon, we are going to have three major reactions in carboxylic acids. The first reaction is the one in which an hydrogen atom is involved. We know that whenever hydrogen atom is involved, it's going to be a neutralization reaction, a salt formation reaction. Over here, what actually will happen is we are going to take a carboxylic acid. That carboxylic acid will react with one of the following reagents. If it reacts with a base, it's going to produce water and salt. When it's going to react with carbonates or bicarbonates, it is going to produce carbon dioxide with effervescence. Effervescence is something we have previously studied, water and salt of the particular carbonate, salt of the particular carboxylic acid. And then we have the carboxylic acid. When carboxylic acid reacts with metal, it's going to evolve hydrogen gas alongside the formation of a salt. Now let's just move on to some nucleophilic substitution reactions. Nucleophilic substitution reactions are the ones in which the OH group is replaced. The nucleophilic OH group is replaced by a stronger nucleophile, a stronger nucleophile like halogens, like halogens, like halogens, uh, OR group, amide group, due to which it forms acid halide, esters, and amides. So in that way, it is going to perform nucleophilic substitution reaction. Now let's just look into the structure. Look into the actual mechanism of how does it happen. Let's say we take an halogenating agent, which is phosphorus pentachloride. These are actually two reactions represented, but we are going, for the sake of easiness, we are going to consider the second reaction, thionyl chloride, reaction of acetic acid with thionyl chloride. It said when acetic acid reacts with thionyl chloride, it's going to produce an acid halide. This is an acid halide, alongside which there would be formation of sulfur dioxide gas and HCl vapors. So this reaction is mostly preferred because that involves the byproducts formation in the form of a gas, due to which it is easier to extract the acid halide. While other halogenating agents can also be used, such as phosphorus pentachloride, trichloride, etc. So let's just move on to an important thing about its mechanism. That how does the entire reaction goes on? Unfortunately, I have got a problem with my pen, due to which I'm only going to write my steps. I'm only going to write the steps down, and I'll be verbally explaining it, um, so that you can understand it. So the first step the first step is the reaction, is the formation of strong nucleophile. Then what actually happens in the first step? There is the formation of a strong nucleophile. This thionyl chloride is having such type of structure. Let me just try to draw the structure. Let's say this is it. This part gains a positive charge. This is actually having a positive charge, right? And on the other hand side, I get a strong nucleophile chloride that breaks down. This positive part goes towards the um, acetic acid, due to which it forms a complex of carboanion, and that, sorry, it joins with the acetic acid, due to which it forms um, an adduct. And that adduct, what actually does in the second step is that adduct in the second step reacts with the strong nucleophile. So the second step would be second step reaction with strong nucleophile. And right after the reaction with the strong nucleophile, what we'll actually get is we'll get a very unstable intermediate. So that unstable intermediate will, what actually it will actually do is, this unstable intermediate will in the third step, this unstable intermediate in the third step will release sulfur dioxide, right? It will release sulfur dioxide molecule and chloride ion from it, chloride and protons. And chloride and proton will combine together in order to form the HCl, and sulfur dioxide would be, and HCl vapors would be evaporated. This is a procedure known as halogenation. This procedure is known as neutrophil substitution. Second type of reaction is very important reaction, the most important reaction with carboxylic acid, which is the esterification. If you were to name it more fancifully, we are going to name it Fischer esterification. Fischer esterification, that is done when carboxylic acids react with an alcohol in the presence of a strong acid or base. So at that point we are going to get an ester, a compound which is known as an ester. So let's just understand the mechanism. This is the entire reaction, we have seen it multiple times as well, but let's just understand its mechanism. The first step in this mechanism is the protonation of carboxylic acid, such that the carboxylic acid is protonated, and then once it is protonated, it then becomes positively charged. It then becomes a positively charged agent, or I would say a carbocation. That carbocation then will react with ethanol in order to produce in order to produce in order to produce a complex, right? We can name it a complex. And in the third step, what will actually happen is, in the third step, let me just move it a bit aside. Okay, so in the third step, what actually happens is, the electron which is present in the hydrogen which is present on the carbonyl carbon will then shift towards the hydrogen, towards the OH group, due to which there would be the shifting of proton happening. Shifting of proton happening. Shifting of proton will happen from the carbonyl carbon to the OH group, due to which it will form an unstable H2O positive ion, right? So this would be the third step. And in the fourth step, what will actually happen is, there would be elimination, because that structure is very unstable because of the presence of an H2O ion. The H2O molecule would be released out, H2O would be eliminated, and the base which we utilize in the proton which we utilized in the first step for the protonation of carboxylic acid from the concentrated H2SO4 would be regenerated. So there is the elimination of H2SO4 and the proton. This is the entire reaction. So now let's just move on to the other part, which is formation of amides. So carboxylic acid can react with ammonia in order to produce amides. This entire reaction takes place in two steps. First, there is formation of ammonium salt. That this is an ammonium salt which is further heated up to a very small temperature to form an amide. So this is how the entire reaction takes place. This reaction takes place in an acidic medium, but if you're going to conduct this reaction in a basic medium, then that's going to actually produce an that's going to produce a sodium salt of carboxylic acid, and that's going to produce an amide, right? And let's just move on to another important reaction which is present over here, that is the reduction. So reduction for reduction, I guess we have two more slides. So over here, if we just take this reaction, carboxylic acid being reduced in the presence of a strong oxidizing agent like lithium aluminum hydride, we will actually get an alcohol from it. This type of reduction is only having the reduction of carboxylic acid to alcohol, which is known as partial reduction. When there's a reduction in the presence of strong conditions like for a strong oxidizing agent, hydrogen iodide, and at a very very high temperature in the presence of red phosphorus catalyst, we are going to get an alkane alongside water and iodine gas. This is another reaction. Now let's just move on to some of the carboxylic acid derivatives. Carboxylic acid derivatives are there, such as acid halides, amides, and esters. So these are having few important reactions that we need to work on. So over here, when we are first going to discuss the reaction of acid halides, when acid halides are going to react with when we are going to perform hydrolysis, whenever we are going to perform hydrolysis of acid halides, we are going to get HCl. If I perform, I don't think so, it's here. So let me just explain it verbally. When we are going to perform hydrolysis of acid halides, it's going to form two main things, HCl and carboxylic acid. And second type of reaction is the reaction of acid halide with carboxylic acid, due to which it forms an anhydride, and that anhydride alongside HCl. And when you're going to react when you're going to react acid halide with alcohol, we are going to get HCl plus ester. So these are three important reactions. After that, we have the reactions of anhydrides. Hydrolysis of anhydrides provides us with two carboxylic acid molecules. That is done in the presence of a dilute mineral acid. And then we are going to react acid anhydride with an alcohol. We will actually get two things, ester and a carboxylic acid as a byproduct. And on the other side, when you're going to react it with ammonia, it will produce amide and and carboxylic acid. These are important reactions of esters. Now let's just move on to a few more other reactions. We have over here the reactions of esters, such that when you're going to perform hydrolysis of esters, when I'm going to perform the hydrolysis of esters, is going to bring me back the parent carboxylic acid and alcohol. So this is how it goes. And but and on the other side, when I'm going to perform the hydrolysis of an ester in the presence of a base, in the presence of a basic solvent, then I'm going to get sodium salt of carboxylic acid and alcohol. So this is important thing. And when we are going to, let's say I take a carboxylic acid and I perform its reduction, sorry, not the carboxylic acid, but let's say I take ester and I perform its reaction with Grignard's reagent. So at that point, when it is reacted with Grignard's reagent, I would first get an acetone. Sorry, I will first get an acetone from the ester, and then I would be getting an alcohol. So this is how the reaction would take place with Grignard's reagent. So right after this, there are final reactions of amide, such that when amide is hydrolyzed, it's going to produce ammonium hydroxide. It's going to produce ammonium hydroxide and carboxylic acid. When I'm going to react amide with when I'm going to perform reduction of amide, it is going to produce primary alcohol and ammonia. And on the other side, when I'm going to uh, let's say I take a nitrile group. When I'm going to react nitrile group with Grignard's reagent, it's going to produce first an imine group, and then that imine group is pretty unstable, which is heated up to give an acetone, and that's how the entire reaction goes on. So these are some of the important reactions which were important to mention. Now let's just move on to. Yes. So alongside that, we have discussed in every organic compounds the preparations of carboxylic acid, preparations of the organic compounds as well. So for carboxylic acids, most of the reactions which are used for the preparation of carboxylic acids are already discussed in most of our previous videos. So do check out those videos if you don't understand through this recap. So we are just going through a very short recap. When we are going to perform carbonation of Grignard's reagent, we are going to get carboxylic acid. Hydrolysis of nitrile gives us carboxylic acid. Oxidation of primary alcohol gives us carboxylic acid, as well as aldehydes gives us carboxylic acid. Hydrolysis of esters gives us carboxylic acids, and there's oxidation of alkyl benzene, side chain oxidation, which gives us carboxylic acids. And oxidative cleavage of alkene, that's something which we have done. We use symmetrical alkenes. We perform the oxidation of symmetrical alkenes to produce carboxylic acids. This is the entire reaction. Now let's just move on to some uses of an important uses of important carboxylic acid, acetic acid. Before doing that, I'm going to tell you few important points about acetic acid, such that its boiling point is 118 centigrade. It's having a boiling point of 118 centigrade, alongside which at 17 centigrade it is going to turn into ice-like solid, which is known as a glacial acetic acid. If you just talk about its physical properties, it is a colorless liquid. Its dilute solution is called as vinegar, and it's a colorless liquid which is having a vinegar-like odor, and it has a characteristic vinegar-like odor, and it is used for flavoring for the sake of as a preservative, as for flavoring, for controlling pH, and on the other hand side, it is extremely soluble in water as well. It is soluble in water, ethanol, as well as ether. Now let's talk about some of its uses. It is used as a solvent for many different reactions. For example, if you just take the example of dehalogenation of tetrahalides, dehalogenation of vicinal dihalides. In dehalogenation of vicinal dihalides, we use anhydrous solvents like acetic acid and methanol, and then we have it is used for the manufacture of pickles. It is used as a flavoring agent. It is used for in medicine for the synthesis of various drugs, and it is also used for making compounds like plastics, polyvinyl acetate, for making polymers like polyvinyl acetate, for making rayon, which is cellulose acetate, and silk are such examples. And on the other hand side, we have its use as a coagulant for latex, coagulant for latex in synthetic rubber, coagulant for latex in synthetic rubber industries. And it is also used as a as a medicine, as a medical irritant. It causes irritation when it is put on the skin, and also it is also used for the sake of preservation, preserving food, for controlling the pH, and for that purpose it is very helpful. So this is all about it. Let's wind it up over here. That's all about this video. Hopefully we'll meet again in another video.